This set of notes gives you Introduction to Rate Laws. So in the last set of notes, we learned about how to actually deal with the different reaction rates. And we learned that rate info can be found by looking at the balanced equation, but it can also be figured out by looking at the effect of initial concentration on the rate of the reaction. Okay, so if I run a reaction multiple times but change the initial concentration, I can oftentimes come up with some useful information about it. So if we take a look, for example, in the data that we have over here, we can look and see that we can find a relationship between the initial NH4 plus and the rate. Okay, so if you go ahead over here, take a look, see if you can figure that one out. Okay, you'll notice that for the reaction, we have both ammonium ions and nitrite ions. And if I look at my experiments over here on the side, you'll notice that the initial concentration of NH4 changes in experiments 1, 2, and 3. The NO2 stays the same. Okay, so with that information, we can go ahead and we can see if there's a relationship. Well, if I go from 0.1 to 0.2, I'm doubling the initial concentration. Same thing, 0.02 to 0.04, doubling the concentration. What do I see happens to the rates during that time? Well, between 0.01 and 0.02, I go from 5.4 times 10 to the negative 7th to 10.8 times 10 to the negative 7th. Hopefully you recognize that that's a doubling, okay? If I go from 0.2 to 0.4, which again is doubling the concentration, I am once again doubling the rate. So what's the relationship between them? In short, when I double the concentration, I double the rate. How about between NO2? Okay, take a look at this data. See if you can figure out what you're supposed to look at there. Okay, so hopefully you're looking at 4, 5, and 6 because that's where those are constant and the initial NO2 concentration is changing. So again, 0.02 to 0.04 to 0.08, we're doubling here again. And if I go from 10.8 to 21.6, that's a double. 21.6, that's a double as well. So in this particular case, doubling the concentration of either reactant doubles the rate. Okay, so if I'm going to write that formally, again, when the concentration of NH4 doubles, the rate doubles, or exponentially, we would say 2 to the m equals 2. Okay, so if that's the case, then m for us to put in there is 1. Okay. When NO2 doubles, the rate doubles. So exponentially, again, we would say 2 to the nth power equals 2. Okay. So again, I'm going to go ahead and n is going to equal 1. Okay. So again, when I double the concentration, I double the rate. Okay. From this data, we can then go ahead and write what's known as a rate law. Okay. So the general form of a rate law, given a reaction where we have a substance and a coefficient, and substances in the coefficient, we're going to basically go ahead and say that the rate is some constant times the concentration of substance A to whatever you determine is the m power times the concentration of substance B times whatever you determine is the n power. Okay, notice only the reactants are involved in this rate law. Okay, so m and n are usually small whole numbers dependent upon the concentration of the effective concentration on rate. Those exponents, m and n, have to be determined experimentally from rate data. You can't figure them out from the balanced equation. You can't do them from anything. What you have to do is you have to have rate data in order to be able to figure out what those exponents for m and n are. Okay, k, the thing out in front, is called the rate constant. Okay, it's just a constant that goes along with any particular reaction, and it depends upon a lot of factors. Okay, it depends upon the temperature. So if I change the temperature, the rate constant is probably going to change. If I change the particle size, that's going to change. So it can change again for reactions under different conditions. Usually temperature is the most common one that they're changing. Okay, so if I change the temperature, the rate constant for this reaction is going to change. Okay, but if I keep all conditions the same, Rate constant is constant. All right, so using that, we said that M was 1 for NH4 and N was 1 for NO2. So I can write the rate law. Rate equals the rate constant times the concentration of the NH4 to the first power times the concentration of the NO2 to the first power. That then is the rate law for this reaction. Okay, those exponents that we have are given a name. We call them the reaction order, and we express them with respect to each reactant. So since the rate law is this, we would say that this reaction or this rate is first order with respect to the concentration of NH4 plus. Again, that's because the exponent there was a 1. It's also first order with respect to the NO2 ion, again, because that is that exponent was also a 1. Okay, so you can express the the reaction orders with respect to each reactant. You can also express the overall reaction order, and the way that you do that is you just simply go ahead and you add up whatever the reaction orders are. So since the rate law was this and this, we just take the two reaction orders, first order with respect to this, first order with respect to that, add them up, and the overall reaction is a second order reaction. Right, so that was talking a lot about how the concentrations affect things. Let's turn our focus now to K, the rate constant. Okay, the rate constant on the front of this is going to basically tell us whether this reaction is a fast reaction or a slow reaction. Okay, so if you have a large rate constant, in other words, if K is big, then it's going to be a fast reaction. If K is small, the reaction is going to be slow. Okay, so how do we say that? Well, this is all relative. So really, we say a reaction is fast once K gets up into the order of 10 to the 9th. Okay, we say it's slow once K gets down to 10 or less, smaller powers of 10. So 10 to the first, 10 to the 0, 10 to the negative first, etc. Okay, what if it's in between there? Again, we don't really usually express that. We're just looking for fast reactions or slow reactions. Okay, in the middle is kind of just in the middle. The other thing that's important about the rate constant is that the units on the rate constant can change. Okay, and they change depending upon the overall reaction order. Okay, so what you need to do is understand that when we calculated rates the other day, especially for a solution, we always came up with the rate units for rate being molarity per second. Okay, so if you go ahead and figure out what the units are on the rate constant, that will give you something on this side, and then you have to look at what are the units on each of the concentrations, cancel things out, and whatever you cancel out needs to come back and equal to molarity per second. We'll show you an example of that in just a second. So for example, in the reaction we've been using all along, we said that rate equals K times the concentration of NH4 plus and the concentration of NO2 minus. Okay? All right. Well, I know that my rate units need to end up being molarity per second. Okay? My units on K are what we don't know they are, or what we're trying to figure out. We know the units on NH4, that's a concentration, so that's going to be molarity. We know that NO2 is also going to be molarity. Okay, so right now I have molarity times the molarity times some other kind of unit has to equal molarity per second. Okay, well, if you'll notice, I got too many molarities on top on this side, so I got to get rid of one of them. So I'm going to put a molarity in the denominator of my rate constant units. Okay, that will cancel out one of those. Okay, the other one is we notice that we don't have a seconds on this side at all, so I'm going to put that on the side over here as well. Okay, so in order to make this work, then my units for my rate constant K are going to be some number of 1 over molarity per second, or molarity to the -1, seconds to the -1. Okay, so that's my units for this particular rate constant in this reaction. Okay, again, why does that work? Because if I have 1 over seconds per molarity. Molarity cancels, and so then my units on this side end up being molarity per second, which is exactly what we want for a rate. That's your basic introduction to rate laws.